We have seen that a common source amplifier using PMOS transistor has the same small signal picture as that using an NMOS transistor, and its characteristics are also largely the same. Any differences between these two are only in the parameter values, okay, because mu n Cox is different from mu p Cox and VTP is different from VTN. You have to use different component values to get the same performance, or if you do use the same component values, let's say the same load resistance and so on, and the same operating point, you will get a different value of gain. Okay, but qualitatively there is no difference in the small signal picture. Okay. Now let's look at the large signal characteristic of the amplifier, with namely the swing limits. Okay. Now this is the PMOS common source amplifier, and in this case, just for simplicity, I will remove this RS. Okay. Although the calculations are exactly the same, even with RS, we always get this additional division of voltage between RS and R1 parallel R2. Okay, I will eliminate that, and I will also assume that C1 and C2 are very large so that we can consider them to be short circuits. Okay. So let's say this is 3 mega ohm, this is 21 mega ohm, so that this voltage is 3 volts and RD is 100 kilo ohms and RL is also 100 kilo ohms. Okay, this is just for illustration. Now this voltage VSD in the quiescent condition is 4 volts. Okay. Now why do we have limits on the signal swing? The transistor can go either into the triode region or into cutoff. So because of this, the value of input Vi that you can apply to the circuit is limited. Okay. So now we will investigate this for the PMOS common source amplifier. The conditions are exactly the same. The condition to remain in saturation is that VSD has to be greater than or equal to VSG minus VTP, and the condition to avoid cutoff, I'll say write not cutoff, is that ID is greater than 0, and these refer to not the operating point values but the total quantities when the signal is applied. Okay. So what we have to do is similar to what we did in case of the NMOS amplifiers. Okay. We have to first find the total VSG, total VSD and total ID and apply these conditions. Okay. At the operating point, we have VSG equals 3 volts and VSD equals 4 volts. Okay. Or if you refer the voltages to ground, the gate voltage is at 21 volts and the drain voltage is at 20 volts. Sometimes for the saturation triode boundary, you specify the conditions in terms of VG and VD instead of VGS and VDS. Okay, that's also possible. So I have written those things down as well. And the current ID is 200 microamperes. That is of course flowing downwards. Okay. So you have to keep this in mind, that this ID in a PMOS transistor is flowing downwards. Okay. Now when the signal Vi is applied, the voltage at this node would be the quiescent voltage, which is 21 volts plus Vi. Okay. Because if you didn't apply Vi, or if you set Vi to 0, this is at 21 volts with respect to ground. Remember, when I say voltage at some node, it is with reference to the common ground node of the circuit. So it's at 21 volts plus Vi. Okay. Now this point is 24 volts above the ground because of the power supply. So VSG, you can easily see, is, if you calculate the total quantity, VSG total is 24 volts minus the gate voltage, which tells you that it is 3 volts minus Vi. Okay. Another way to think about it is that if Vi it has a positive value, then this voltage increases and the source voltage is remaining the same. Okay, so the source gate voltage actually reduces because the gate is going up. So already you see the crucial difference here. In case of an NMOS common source amplifier, this would have been 3 volts plus Vi, or the quiescent VGS plus Vi. Now we have a minus. Okay. Now the voltage here at the drain, the quiescent voltage is 20 volts. Okay. And what is the incremental voltage at the drain? That we get from the small signal picture. Okay. So we have Vi, and this is the gate, drain, and source of the MOS transistor. We have RD and RL. So VGS equals Vi. Okay. So this is GM VGS, and the drain voltage with respect to ground, which is the small signal ground, is minus GM RD parallel RL times VGS. Okay. And in this particular case, GM is 200 microsiemens and RD and RL are 100 kilo ohms. So this turns out to be minus 200 times 50. So that is minus 10 times Vi. Okay. So the incremental voltage at the drain is minus 10 Vi. So the incremental voltage here is minus 10 times Vi at the drain. So the total voltage is 20 volts minus 10 times Vi. Okay. So VSD, you can see, is 24 volts minus this. 24 volts minus this whole quantity. So VSD total is 4 volts plus Vi. Again, you see a reversal of sign. Okay. And finally, what is the incremental drain current? You can see that this incremental drain current GM-VGS is going from drain to source. But here, the total drain current is going from source to drain. Okay. The incremental drain current is GM times VGS going into the drain. Okay. So the incremental current coming out of the drain is minus GM times VGS. Okay. So the total drain current is 200 microamperes minus GM VGS or minus GM VI, because in this case VI and VGS are the same. Okay. There is 200 microamperes minus 200 microsiemens times Vi. Okay. So you see that the crucial differences lie in these signs. So what does that mean? First, let's try to keep the transistor in saturation region. It will be in saturation if VSD is greater than VSG minus VT, and VSD total is 4 volts plus 10 times Vi, and in general it will be VSD at the operating point. I'll write it as Q for quiescent point, plus the gain of the amplifier GM times RD parallel RL times Vi, and if you have some RS, you also have to include the division between RS and R1 parallel R2. This has to be greater than VSD total, which is 3 volts minus Vi in this case. Okay. And minus the threshold voltage, which is 1 volt. And in general terms, it will be greater than the quiescent source gate voltage. Okay. And I'll write minus Vi. Again, if you have a division between RS and R1 parallel R2, you have to include that here, minus the threshold voltage. Okay. So what do I get out of this? So I take this to the other side, I get 11 Vi should be greater than or equal to 3 volt minus 1 volt minus 4 volt, which is minus 2 volts. Okay, or Vi has to be greater than minus 2 by 11 volts. Now, if you recall, in case of the NMOS common source amplifier, the saturation condition was setting the upper limit for Vi. Okay, now it sets the lower limit for Vi. Okay, you can see that Vi has to be greater than minus 2 by 11 volts. Why does this happen? Here, as Vi becomes smaller, the gate voltage becomes smaller. If the gate voltage becomes smaller, the source gate voltage becomes bigger and the current through the transistor increases. As the current through the transistor increases, the drain voltage increases because that current is going into the parallel combination of RD and RL. Okay. As the drain voltage increases, the gate voltage is falling, the drain voltage is going up, so it's going towards the triode region, and the triode region saturation boundary actually sets a negative limit for Vi. Okay. So that's the difference. Because the polarities of currents and voltages are reversed, the swing limits are opposite in case of PMOS as compared to NMOS. Okay. And again, I'll write it in general terms. Vi has to be greater than or equal to, so all these are greater than or equal to VSGQ minus VSDQ minus VTP divided by 1 plus GM RD parallel RL. I have already explained why these terms come about. In case of the NMOS amplifier, we have 1 plus GM in the denominator because the gate voltage is changing by 1 unit, whereas the drain is changing by gain units. So the gate drain voltage is changing by 1 plus gain units. And if you look at the numerator, this difference is the quiescent gate drain voltage, or the negative of the quiescent drain gate voltage. Okay. So if the drain is well below the gate, then the separation will be large and you will get a large swing limit. Okay. In case of NMOS, it's the opposite. You want to have the drain to be well above the gate voltage so that there is a lot of room for it to fall. In this case, you want the drain to be well below the gate voltage so that there is a lot of room for it to rise. Okay. And similarly, if you apply the cutoff condition, we want ID total to be greater than or equal to 0. And again, as I explained earlier, we could also have used the condition based on the source gate voltage. That is, the source gate voltage should be more than the threshold voltage, but by convention we use this because we can also use this with bipolar transistors. Okay. And what is the total drain current? That is the quiescent current 200 microamperes minus 200 microsiemens times Vi should be greater than or equal to 0, and this tells you that Vi should be less than or equal to 1 volt. So earlier, in case of NMOS common source amplifier, the cutoff condition was imposing a lower limit on Vi. Now it imposes an upper limit. Okay, because as Vi becomes more and more positive, the gate goes up, the source gate voltage falls. Okay. And the drain current goes on reducing, and at some point it will enter cutoff. Okay. And in general terms, the total drain current would be the quiescent drain current minus GM times VGS, and this has to be greater than or equal to 0. So, and in our case VGS equals Vi, so this is GM times Vi. So Vi has to be less than or equal to IDQ times GM. Okay. In summary, the small signal picture of NMOS and PMOS common source amplifiers is the same, and this is true of every other type of amplifier. If you look at NMOS and PMOS, small signal wise they will be the same, large signal wise they will be different. Okay. The swing limits in particular are the opposite. Okay. If in some circuit saturation imposes an upper limit in the NMOS amplifier, it will impose a lower limit in the PMOS amplifier, and similarly for the cutoff. Okay.